All right, everybody, we're going on to section 6.3 today. Section 6.3 is all about integration by parts. So there's a formula involved here. There's a whole bunch of stuff that you just need to, I hate to say it, but there's some stuff that you need to memorize in order to do this. So to start this off, this would have been your do now if you were in person. I would highly recommend pausing the video and trying this out, and then coming back together, noting that we are using the product rule to find our derivatives on here. So product rule is important, making sure that you get this right. Remember, product rule is left to right plus right to left. Important stuff for us to know here, because integration by parts, or as this book puts it, anti-differentiation by parts, this whole process is about undoing the product rule. Like I said, there is going to be a formula that you're going to need to know for this one, and that formula is going to be derived from the product rule. So we are starting off with just the product rule written out for us. I completely copied this product rule from the rule sheet that I gave you guys in chapter 3. We have the derivative of a product is left d right plus right to left. In order to get the integration by parts formula, the first thing that we're going to do is clear out the dx's. To clear out the dx's, well, when you learned this operator, the d dx, I told you it wasn't a fraction unless it's convenient for us to think of it that way. It's convenient for us to think of it that way right now. So we're going to multiply by dx on both sides so that we can just clear out all those dx's. So we're left with d uv is equal to u dv plus v du. Cool so far? The reason we do this, we can now apply the integral to both sides of this equation. So now I'm just going to go in and I'm going to slide that integral symbol onto both sides here. So now it's important to make sure that I put the integral symbol around the entire quantity on the right-hand side there. The left-hand side, now this becomes the integral of 1 duv. Now we know when we anti-differentiate a constant, we just have to slap the variable on the end of it. The variable here is the product of u and v. So the antiderivative of 1, where our dummy variable is uv, is just going to be uv. So that becomes uv equals, over here we have to use the sum property of integrals. We will have the integral of u dv plus the integral of v du. Now here's where we run into a big issue, because those variables don't match on the right hand side. We've got a u and we've got a v. We've got a v and we've got a u. Since they don't match within each individual integral, we actually can't calculate the integral. But this is actually the formula for this. So here, all I have to do is subtract the integral of v du from both sides, and we get uv, ugh, that did not come out looking right, but I'm not going to restart my whole video just for that little bit. I'll just erase it. uv minus the integral of v du is equal to the integral of u dv. This is the integration by parts formula. You have a product within an integral, and you use this formula in order to figure out what the integral is. Generally, this is usually written in this order, just using the symmetric property of equality. We have the integral of u dv is equal to uv minus the integral of v du. And I'm not sure if I'm the only person on the planet that does this, but when I see v du, it just makes me chuckle. To call that voodoo. So I think of this as the integral of u dv is equal to uv minus the integral of voodoo. Just makes me chuckle. Yeah, there's work written out step by step for us. And there is the formula. You need this formula. You need to memorize this formula. Reconstructing the formula every single time is going to take, every single time you use it is going to take way too much time. So you need to have this down. and you need to memorize it. That's why I think calling this part right here voodoo, it both makes me chuckle and it makes me remember it. There is an acronym that's going to be useful for you guys, and that acronym, I read it as LIPET, because that's how the I works, where that E after the P makes the I long. But apparently I'm alone in that, and every single other calculus teacher that I've ever geeked out with has called it LIPET, but whatever. Some of your professors aren't gonna like this. Some of your professors want you to get a feeling for what the U is. This right here is the order in which we choose our U. And this is going to make a little bit more sense when we start to actually do this. But we run through this cycle. We look for logarithms. If there is a logarithm, we use that as our U. If there's an inverse trig function, we use that as our U. Well, sorry. If there's no logarithm, we look for an inverse trig function. And then we use that as our U. If there's no logarithm, no inverse trig function, we use the polynomial as our U. If there's none of those three things, we would use our exponential function as our U, and last resort is to use a trig function as our U. AP never really has you do any problems where the trig function or the exponential is going to be your U choice. There are some actually cool strategies around that, but since AP never asks that, I'm not going to go over those strategies, but again, they're pretty cool. If you want to see them, maybe come during office hours. If I'm not busy, I'll show it to you. All right? So let's do some U substitution problems. We're going to do that one on the left. The integral of x sine of x dx. Now that we're seeing two problems that are integration by parts problems, I'm going to tell you how I know that they're integration by parts problems. They're integration by parts problems because we have a product in the integral. Remember, the integral formula was that integral of u dv is equal to uv minus the integral of voodoo. So that integral of u dv implies that we're looking for products. Even further, this is a product rule where u substitution would not work. Like, I don't see any compositions of functions here, so I'm not going to use u substitution. So it's kind of like when you're doing integration, you have an order of choices that you make. If u substitution's not possible, you go down another rung on the choice ladder, and you go to integration by parts. Now, integration by parts, we start by declaring what our u is and what our dv is. To declare our u, we go through that acronym of LIPET. Do we see any logarithms? Let me pull myself up here. Do we have any logarithms? No. Inverse trig. Do we have any inverse trig? No, we have a trig. Now this next one is tricky. Remember, I told you I'm not going to do any exponential or trig, so we know that our choice is probably going to be the polynomial. So we got no logs, no inverse trig. We're looking for a polynomial. Our polynomial here happens to be a monomial. The monomial here is x. So whenever we're looking for a polynomial, we're looking for some function where it's like x to a power, and you can have sums of powers of x's. Okay? So looking here, we say that our u is our polynomial. We are going to both put down our u and our dv. Remember, in the formula, when we start off the formula, we have integral of u dv. We just said part of this expression, the u is x. The rest of that integral notation is going to be dv. So sine x dx. We also want to find du and v. Now this is tricky because what goes on in my head, we have to think both forward and backward. We need to differentiate and we need to integrate to complete this. Now the reason why we need du and v, look back at the formula. We have uv and v du over here. So far, all we know is what u is. To find du, take the derivative of u and tack on dx. to find out what our v is. Anti-differentiate dv. The dx is going to go away. Well, I guess not anti-differentiate, just integrate that. The integral of sine. We got to think of what gives us a derivative of sine of x. What gives us a derivative of sine of x is going to be negative cosine of x. I like to put all of this in a box just to say this is my scratch work. Again, it's kind of like when we did u substitution, we had to say u equals and then du equals, all that stuff. We keep it separate from our problem. And now we're going to take the integral of x sine x dx, and we're going to fill out the formula of uv minus integral of v du. So the first part of that formula is not in an integral symbol, and it is u times v. So u times v would be x times negative cosine of x. Next part of the formula is minus integral of voodoo. Minus integral of v negative cosine x times du dx. So that's the integral problem that we have. The integral of x sine of x dx is equal to x times negative cosine of x minus the integral of negative cosine of x dx. All right, so now, really if I had more space, I would probably just keep going over, but I'm running out of space here, so this just loops back over here. I'm just putting it in this order because my space limitations on my paper on my board. I'm gonna simplify all this. I've moved that negative out front, negative x. Cosine of x minus negative, so plus integral of cosine of x dx. Now notice that first term does not have an integral symbol in front of it. If it has no integral symbol, guess what I don't do? That's right, I don't integrate it. So the next part of this problem is going to be negative x cosine of x plus, now I have to integrate cosine of x. The integral of cosine of x, what gives me a derivative of cosine of x, is sine of x plus c. All right? Now, we do like to make sure that we have the right answer, right? So we want to go through and we want to make sure that we can have a check step. I kind of showed you the check step when we were talking about u substitution. We don't always do it because we don't always have time. But let's check it here. So I'm putting this in red. I thought I changed that to red. Stupid board. Come on. Check step. Take the derivative of this. The check step is, what is the derivative of negative x cosine x plus sine x plus c? And we just get it to a point where we recognize that this expression is the same as the original integrand. So looking at this, I know that, let's see, the first term here, I'm going to have to use product rule on this. So I've got, I just dropped a yardstick. Move that out of the way. Product rule, I've got left, negative x, d right. The derivative of cosine is negative sine of x plus right to left. So the right is cosine of x times the derivative of negative x would be negative 1 plus the derivative of sine of x is cosine of x. Derivative of c, since it's a constant, it drops out. Well, let's see here. This becomes x sine of x. Here we have minus cosine of x plus cosine of x. It seems to me those cross off, and now I can see that expression is the same as that expression right up top. So I've just checked my work. So the answer is, just to be clear, let's just make sure we have the answer down, right? The answer is going to be this right here. The red stuff at the bottom was just for me to say, hey, Woj, you did this right. Let's check this one over here. We got another one. Evaluate integral of x e to the x. All right, let's put a bar down here so that we don't get our work commingled here. Okay, again, we run through LIPET. Logarithms. 9. Inverse trig. Nope. Polynomial. Yep. We have a polynomial. That's our u. Our u is x. Our dv is everything else. E to the x dx. Finding du. 1 dx, or just dx. V, integral of e to the x is e to the x. Put it in a box to keep it separate. We now fill out the formula. uv. By the way, I like this exact ordering where I put u, dv, and then immediately under there, I put those, because now I have uv is drawing this like little diagonal right here. And then vdu is just the bottom row right there. It makes it easy for me to physically see where all this stuff is so that I don't necessarily have to remember that formula. So I've got u times v minus integral of v du e to the x dx. And the only thing left for me, I know that this first term, since there's no integral symbol, I don't integrate it. I've just got e to the x minus, x e to the x minus the integral of e to the x, which is just e to the x plus c. There's my answer. I'm done, unless I want to check to make sure that I'm right. So down here, d dx of x e to the x minus e to the x plus c. Again, we know the plus c is going to cancel out. I have left d right plus right d left minus derivative of e to the x is e to the x. Oh, hey, it looks like those cross off. And I'm left with x e to the x, which is my original integrand. So it matches. We good. We just checked it. Again, you don't have to do the check step unless you unless you have the time and you like to make sure that you're right. There we go. How's about this one? This is my favorite one. Now, last section, this was a rule. It was on page, I think it was 332, if that sounds about correct. Yeah, definitely 332. You actually had a formula right in there. Let me just see. See, it's right there. Now, I did say I don't memorize this one because that's too much for me to memorize. So instead, I look at it as an integration by parts formula problem. This is an integration by parts problem where I have to choose my u. I hate writing in red. It's writing in blue. There we go. I run through my LIPET. Any logs? Oh yes, there is a logarithm. There is a logarithm. ln of x. So whenever I see an integral with a logarithm, I automatically know that this is going to be an integration by parts problem. My dv is going to be everything else in the integral other than what my u was. My u was ln of x. My dv is dx. du, I have to know what du is. Let's see, the derivative of ln of x. Oh yeah, that's easy. 1 over x dx. V, the antiderivative of dx, is just going to be x. Put it in a box to keep it separate as my scratch work, and then fill out the formula. uv, so we've got ln of x times x minus the integral of voodoo, so x times 1 over x dx. Simplify this to make it a little bit easier to work with. Like first off, I see ln of x times x. We don't generally put the x at the end. We should put the x at the front. It actually pained me when I was writing it out to put that x over there, but I wanted to keep it in the order of u and v. Minus integral. Well, over here I see x times 1 over x. X times 1 over x cancels out to just 1 dx. And again, just like last time, I want to find just the integral. First term stays the same. X ln of x minus the integral of 1 dx is just x plus c. Again, that's a formula that is in right over here. It's the same thing that I just wrote up on the board, but it's much easier to do it as an integration by parts problem. And there's also like all sorts of other ones, like just thinking about this, just spitballing here. Same kind of problem as x, ln of x dx. That's another common one that you would see, where you would have your u again is ln of x. Your dv, in this case, would be x dx. My du would be 1 over x dx. My v, the antiderivative of x, is x squared over 2. These are my favorite kind of integration by parts problems. So now I have uv, so that's going to be ln x times x squared over 2 minus integral of v du, so x squared over 2 times 1 over x dx. Simplifying the crap out of this to make it easier to work with, I would have x squared ln x over 2 minus the integral, looking here, one of those factors cancels off with this. We now have x over 2 dx, and now we really just need to antidifferentiate that x, right? This becomes x squared ln x all over 2 minus, well, that over 2 can just be carried down as a factor as 1/2 times the antiderivative of x is x squared over 2, doing that n plus 1, x to the n plus 1 over n plus 1 plus c. So my final answer, x squared ln x over 2 minus x squared over 4 plus c. Again, those types of problems, they just make me geek out whenever I see an ln in my integrand. They're just fun to do. Come on. There we go. So you can see there's my work again. Oh man. They can't always be this straightforward, can they? You might be able to figure out what's going to happen in this problem. It's going to have multiple parts to it. So that does happen, but we can bear with it. So look in here. We're going to run through our LIPET. Do we have any logs? No. Do we have any inverse trigs? No. Do we have any polynomials? Yes. So that's our u. Our u here is going to be x squared. Our du is going to be everything else. Our du, nope, dang it. Why did I say that? Why did you guys let me say that? You're supposed to interrupt me and say, no, dummy, it's not supposed to be u and du. It's supposed to be u and dv. dv is everything else in there. I know, you guys were saying that at home, but you couldn't time travel back a week and tell me that I was doing it wrong. Now we have to calculate du, right? Our calculation of du is going to be 2x dx. Now this v, I know it's easy to forget what we're having with our v here, but since we're going from dv to v, we want to anti-differentiate the e to the x, which happens to not matter because it's e to the x. E to the x is both its own derivative and antiderivative. So now we're going to fill out the formula. We fill out the formula, we've got uv, so uv is x squared e to the x minus the integral of v du, e to the x times 2x dx. We simplify this stuff, or rearrange this stuff to make it a little bit more readable. So we're going to have x squared e to the x minus integral of 2x e to the x dx. And when we get here, we try to evaluate this integral, but we see that we have a product. And again, whenever we see a product inside of our integral, first thing we try is we try our u substitution. U substitution is going to fail here because we do not have any compositions of functions. So we're skipping the u substitution. We go directly to our next option is this whole stuff we're doing today. So we're going to use our integration by parts. What I'm trying to say here is we've just got another layer of our integration by parts. So we're going to have u is equal to, let's see, do we have any logarithms? No? Okay. Do we have any inverse trigs? No? Okay. Do we have any polynomials? Yes, we do. I'm going to use my 2x as my polynomial, which would make my dv into my e to the x. My du, therefore, will be 2 dx, and my v, the antiderivative, oh, sorry, e to the x dx. My v will be e to the x. I like to put this in a box. Again, I put it right under here so I don't get it confused with the u and the dv from over here. And now I'm running out of space, so I'm going to have to skip over the box and just go right here. I now have x squared e to the x minus. Now this next part is important. Since all of this is stuck together, I want to put parentheses. And now I'm going to do my uv, 2x e to the x minus the integral of v du. So e to the x times 2 dx. Close my parentheses. Now I'm just going to clean this up a little bit. This becomes x squared e to the x. I'm going to distribute my minus here. So this becomes 2x e to the x minus negative becomes plus integral of 2 e to the x dx. Okay, so now I look at this and try to find this integral. Well, 2 is just a constant multiple, right? So I'm really just looking for what's the integral of e to the x. This becomes x squared e to the x minus 2x e to the x plus 2 e to the x. And we got to remember our plus c. Please don't lose points because you forget the plus c at the end. That is very important. And we're actually done now. Notice we had to do 2 steps on this one. I will tell you that if your polynomial is your u choice, the number of steps you have to do matches the degree of the polynomial. So if we have x to the 4th, we're going to have to do this 4 times. If we have x to the 20th, we're going to have to do this 20 times. Now there is a nice part about this. There's a trick, a nice little way that you can do this a lot faster and keep track of it, and it is called tabular integration. I will show you tabular integration here, but the tabular integration comes from when you look here, our u's. The du from this first step becomes the u for the second step. So when we're finding our du's, we're going to differentiate until we can't differentiate anymore. If I differentiated this, I would get a 0 next time around. Now, keep in mind, when we were going from our dv to our v, it was kind of wonky here because we were using e to the x. But here, we are anti-differentiating. So the antiderivative of e to the x becomes e to the x. This antiderivative is now over here. And then we keep anti-differentiating. What I'm trying to say here is we choose our polynomial and we differentiate it until it don't differentiate no more. We take the rest of it and we integrate it until we run out of steps here. So the way that that's going to work here, let's see, tabular, I believe, come on, no, not that, tabular integration. What we do, this works if we have our u choice is a polynomial. Anything else we don't want to use tabular integration. Since we're using our polynomial as our u, we write that polynomial down in our first column. In our second column, we're going to put the other factor in the product. So we've got x squared in the first column, we've got e to the x in the second column. In the first column, we're going to take derivatives, like I said, until it don't differentiate no more. So we're going to have 2x, 2, and then 0. We want to do this until the first time we get a 0. Now, in the second column, keep in mind it's a little bit tricky here because we have e to the x. We want to integrate in the second column. So differentiate first column, integrate second column. We'll have integral of e to the x is e to the x, e to the x, e to the x. Hopefully tomorrow we'll have some more clear examples of using the tabular integration. And now what we're going to do, we're going to connect with diagonal lines. First to second, second to third, third to fourth. And above each of these lines, looking back here, when we did the integration by parts, notice how the signs flip-flop here. We're going to reflect that in the tabular integration. We're going to start with a positive, go to negative, go to positive. Those signs mean what operation we put in between each term. These diagonal lines mean multiply them together. So this, using tabular integration, becomes x squared e to the x minus 2x e to the x plus 2 e to the x, and of course plus c. Notice how this answer is the same as this answer. They get you to the same part, or the same point, so they are equally valid. This one is more of a, like using the tabular integration, it is more of an algorithmic method for completing the integration by parts. So some, I know if you take calculus in college, your professor will probably look down on you for using tabular integration. They might not even teach it, but it is an okay way when you have more than one step. And again, it only works when your u choice is a polynomial. Let's see. There you can see I actually call it out as differentiate this column, integrate this column, and make sure you alternate your signs on those diagonal lines. Oh, here we go. Here's one that makes it a little bit more obvious what's happening here. Again, we run through our LIPET. This is only going to work if our u choice is polynomial. No logs, no inverse trig, but we do have x cubed. So I'm going to put x cubed down in my first column. I'm going to put the other factor in my second column. So I've got x cubed cosine of x. I'm going to run down this column until I can't differentiate anymore. 3x squared, 6x, 6, 0. And you want to make sure that you go all the way till you get to a 0. Just put 0 down once. If I kept differentiating, I would just keep having 0. So it's useless to go anymore. Now again, remember we are anti-differentiating. So the antiderivative of cosine is negative sine. The antiderivative of negative sine is negative cosine. The antiderivative of negative cosine is sine, and the antiderivative of sine is cosine. So again, the SIGN of the SINE is going to be paramount here. Connect with my diagonal lines, first to second, second to third, third to fourth, fourth to fifth, plus, minus, and now diagonal lines mean multiply, sign in between means the sign. So look in here, I've got x cubed times negative sine of x. Well, positive times negative gives me negative x cubed sine of x minus, but we've got positive times negative, so this becomes plus because I have the minus minus. 3x squared cosine of x plus 6x times sine x. And finally, minus 6 cosine of x. And who's going to remind me? What am I missing? What am I missing? Always, since we're doing our indefinite integrals, we want to have a plus c. So again, the person that likes to understand math in me does not like this method for the algorithmic factor of it, but the side of me that doesn't want to do this whole integration by parts 3 times really appreciates this tabular integration. All right, so I guess we had to bring this one up. All right, so this one is actually a beautiful problem in that it allows me to do integration by parts, and in the middle of integration by parts, I'm going to do a u substitution. So here, I'm going to run through my LIPET. And remember, I told you guys we don't really use exponential functions or trig functions in this course. They do have like cool applications, but again, we're not going to use them here. But we haven't done inverse trig yet, so let's do it now. Looking here, I see that there are no logarithms. There are no, oh wait, there are no logarithms, but there are inverse trigs. So my u here is going to be my inverse trig. My dv, therefore, is going to be everything else, dx, du. Might have to pull out my rule sheet for this one, but I happen to remember that the derivative of arc sine is 1 over the square root of 1 minus x squared. Since this is a differential, I need dx. V can equal x. Alright, cool. Box it up. Whoa. How did that happen? Equals uv. I'm going to rearrange it just to make it easier for me to see. I'm going to put it as vu. I hope you don't hate me for that one. X arc sine of x minus integral of v du, v being x, times 1 over the square root of 1 minus x squared dx. If I want to, I can make this look a little bit prettier. So I'm going to have x arc sine of x. Good news, we're already done with the first term. Yay! Bad news, the second term looks awful. X over the square root of 1 minus x squared dx. Now here's where we have to go away from the previous strategies that we've used here. When we've done integration by parts so far in this video, we've gone and done integration by parts again, but we want to run through our little choice ladder here. First thing we look at, we don't know what this derivative is just off the top of our head, so we can't just write down the answer. So we look for alternative strategies. The first strategy you should always use is u substitution, and u substitution comes up when you have a composition of functions where the derivative of the inner function is in there. So what I'm looking at here, the composition of functions, is that square root of 1 minus x squared. So I'm going to say my u is 1 minus x squared. Now keep in mind my over square root of that u, that's my f of u. So I'm going to ignore, just like we did in the last video, I'm going to ignore this divide by square root of 1 minus x squared. The rest of that is x dx. When I take this derivative, I'm going to get, I meant to make that blue. My du is going to be negative 2x dx. I look back up at my problem and I can see I've got x dx, which is like this except it differs by a constant factor. I can make this into negative 1/2 du is equal to x dx. So now that's my work for my u substitution. This problem up here now becomes, let's go over here so we have enough room. X arc sine of x minus the integral of, instead of x dx, I've got negative 1/2 du over the square root of u. Well, now I see that that has one variable in it, making this a little bit more integrable, where I can see what the integral is. Again, that first term, I'm done with it, so I'm just copying it over. I can move this negative 1/2 out from it. So now this becomes plus 1/2 times the integral. Since I've got square root in the denominator, I'm going to have x to the negative 1/2. No, not x. Why did I put x? That variable is not x. That variable was u to the negative 1/2 du. And now I can see this is just a power rule problem. So again, first term just carries down. X arcsine x plus 1/2 u to the negative 1/2 plus 1 divided by negative 1/2 plus 1. Well, negative 1/2 plus 1, that's just 1/2, isn't it? Boom, boom. I guess plus c. What I'm left with here is just going to be x arcsine of x plus, I guess now I have 1/2 up here. This would be the square root of u plus c. Remember, c is an arbitrary constant. Other than c, what irks me about this problem is I have x's and u's. I have to go back and I have to sub in my u. Now it is important to remember which u this is. This u is not this u. It is the u for my u substitution. So my final answer is going to be x arcsine of x plus the square root of 1 minus x squared plus c. Whew. That's a fun problem because it allows us to do multiple strategies all at once. I can calm your nerves by saying it's not a common problem for us to have to do. I think that's the last problem that we had. Am I right? Of course I'm right. So here is your practice work. I will see you all tomorrow.